So,
Yes.
yeah, today's my topic is platforms for solar system exploration. So, I would like to take you through or introduce you to this particular subject through one of the books which has been written by authors across the globe, and they have tried to define for the next 4 decades the kind of missions or planetary exploration we as a human beings situated on this planet Earth are supposed to conduct and explore this scientific mission. So I have taken the some of the materials from this book, and they build this planetary exploration using 4 pillars, and they identify why these pillars are needed and how they are interconnected. So for any system or any scientific exploration, you need to have science goals. That forms the first pillar where you are going to ask key science questions. And when you have some science questions, obviously you need to do some measurements, and you cannot do all the measurements under the solar system or under the sun. So you will define particular mission targets and types, and based on the mission targets and types, I want the moon, but I need to build technology to go to the moon or get the samples from back from the moon. So that forms the third pillar, which we will be concentrating on this particular presentation, which is enabling future technologies. And the fourth pillar is like it is not only the space platforms which need a lot of infrastructure, but even ground system. In fact, it's a intellectual infrastructure as well as physical infrastructure and cooperative infrastructure between the countries, which will be needed for identifying the missions and how do we carry out those missions. So as I have circled the pillar 4, which I'll be concentrating on in this particular presentation. So let me take you to, I think you have been listening to all these topics where the key science questions. So I just want to summarize so that I build a base, and from there I'll take you to the technologies which will be needed. So basically we are going to ask some 6 questions. So we want to understand, explore the diversity of the planetary system, and you can see even the solar system itself has terrestrial planets, then you have gas giants, and then you have icy planets. So why they are so diverse? So this particular diversity is the question number 1. And why these are all different architecture, how did they form? So that's come to the question number 3, origins of planetary system, how do planetary systems work? Because we are looking for possible life in this universe. So these form the basic footprints or basic what do you call framework for life to exist. So that is how did Earth become habitable, and are there any Earth-like systems in the other solar system or other star system? So that is what is the aim of our key science questions. But these are questions, so you need to have measurement or observational techniques. So the presently identified 9 destinations are the Earth Moon system, Venus, Mars, Mercury, gas giant system, ice giant system, small bodies, heliospheric boundary, interstellar medium, extrasolar planetary bodies. So how do we do measurements? So what are the observation techniques? So there are Earth-based telescopes, but they have their own uh, limitation in terms of how much we can observe or how much we can do the measurements. Then you have Earth bound, like in the planet, to take care of the atmospheric problem. So you have given the telescopes either orbiting the Earth or orbiting some L points. So then you have robotic exploration where you can do flybys. Then you have orbiters, lander, to do in situ measurements. Then of course you want to see the samples for yourself and feel it and do much more elaborate tests which are not possible. So you cannot send a whole lab to the planet to do the experiment. So you need to bring the sample. So it's basically economics. So which will further enable for us to do the human exploration. So the 7 type of missions which are covered are observation from Earth, meteorite collection, planet, small body, flybys, orbital exploration, landers, rovers, and sample return, finally ending up with human exploration. So now coming to the pillar one. So now we know science questions to the measurement. So we are going to lay out like it's a systematic way of asking the questions, like first question, second question, third question, and what measurements you want to do for a particular nine destinations we have listed here. Then go to the pillar two, where from these measurement, what are possible right now? So can we divide it into time frame, like next 2 decades up to 40 and 40 to 60? So this is how you can differentiate what is possible and concentrate on enabling or developing the technologies needed for that. So this forms the pillar two. And pillar 3 and 4 are like, once you have the mission requirement, for example, I want to bring sample from for example, say Mars. So you need sample collection, which is an advanced instrumentation, and precisely bring the samples back to the place where you can launch it from. And for that, you need to have mission architectures, because you have limited resources in terms of how much you can put into the orbit. So you need to have mission architecture, whether they will combine and go there, or like you will have a two different set of mission or a single mission. So this is the architecture. So these are nitty-gritties, what they call. Devil is in the details. So these are the details which you need to work out. And system level technologies. So are there sufficient like propulsion systems technologies do we have? Do we have extreme environment and extreme conditions of the planet where it can work? And if you want to have a long-term presence and exploration, then you need to have sustainable exploration. For that, in situ research utilizations are very essential. So you need to able to generate the propellant from the surface and come back, and you need to sustain the human being. For that, you need oxygen life support system. And any of these technologies can happen only when you have disruptive technologies. And as new young generation of people come into the space exploration, so you are going to have disruptive technologies, so which have been a very latent technologies in some other areas, can become a very important technology for exploration, and which can be a game changer. So we are looking for game changer technologies in terms of exploration of the solar system. And of course, the pillar 4, which I'll not dwell here much. And this is a very, when you look into this particular map, we where all places human beings have been in terms of their presence through their system and technologies. So it's a beautiful map which tells like how many countries visited moon, and how many satellites we had fly by, and how did we orbit. So this is it's a very like a compact slide with so much of information, but I just wanted to show the beauty of like past 50, 75 years of exploration captured in a single shot. And I have another one which tells like from the past 1950s when we started. And on the left side, you can see so many missions were there to explore the sun, even though it was fueled by Cold War. But as a for a human, like for science exploration, it gave a lot of opportunity for us to reach various destination in the planetary system or in the solar system. And as you can see in the right side, so and one very important aspect to see here is a lot of private companies, so it is not limited now, the space is not limited to the governmental agencies with a lot of funding. So even private agencies are coming up with the support of government. They are able to explore the planetary solar system. And I say future is very exciting, because this next slide will show up to 2019, so which are all the missions which are coming. So and I was very happy to see like mom 2 here, and lunar sample return from India here, and Chang'e 6, which has been launched some in a past couple of days. So it's a very exciting future for all of us. So in general, when now like we know what exactly we intend to achieve or measure, but how this exploration will progress. So the exploration will have either remote sensing from Earth, Moon, or L1 points. And Aditya is a very good example of a space platform where we have observation of Sun from L1 point. Then you have interplanetary or interstellar cruise. So and planetary flybys, planetary which have been being used, planetary or satellite orbiter, and single platform. Up to this, we have been using and we have sufficient hold on as a human being. When I tell we, it is all as a human being, we have sufficient hold as a technologist on these platforms. So whereas multi-platform pros, penetrators, and small satellites is another area which needs to be explored so that it is cost effective. The missions are cost effective, and nano satellites, and in distant future maybe chipsats will be exploring this, and landers on planetary bodies or satellite surfaces, lander with mobility, example rover. And you have seen helicopter, Mars helicopter, which did a fantastic job. And you have travelers and balloons like Venus. If you want to do atmospheric study of Venus, then you have balloon system. And some of the liquid surfaces can be explored using submarines. And later, once you explore in situ, then you are bound to return some samples from there for analysis on at Earth. So this is one sample architecture. So I'm right now I have taken you from the science background. Now we are moving slowly towards the technologies needed for, and so that starts with a sample exploration architecture, which is provided here. So as you can see, you need either commercial launch vehicles on the left hand top corners. You can see large human rated rockets will be needed, and it is possible, and we should envisage in an international cooperation for these things. And have a crew vehicle and a reusable human lander where multiple sorties are possible with this particular lander, wherein you have a fueling station in orbit, so which can fuel, and you can keep continuing this exploration quite cost effectively. So you will have, as like before humans land on the surface of moon, so you will need small robotic landers, then you need unpressurized rovers, then you EVA suits, and medium sized cargo landers. So before we go there, we should be able to have our supplies there. So you'll have cargoes and small pressurized rovers which will explore the surface of moon. And then you need to generate power, so you might need power stations there, and a communication tower, so that all the satellites, they don't need to carry the communication. Then you the major and very important, as you come to the right side of your slide, are ISRO ISRU pilot plant. So this is where you need, how do we use the in situ resources to generate either oxygen or build habitats so that humans can live there, and have an oxygen generating system, and probably generate fuels from there, so that it can be used for further as a launch pad. So long duration habitation are needed. So this is a simple architecture. So all these things is possible only when you start, like when you go to the drawing board, and it starts there, like which all the systems are needed to make this or enable this particular architecture. So generally, which are the enabling technologies? You have entry, descent, landing, and ascent. So if you want to bring back the humans, ascent is going to be, and it has been shown successfully that entry, descent, and landing, and a precise landing is possible with even our own Chandrayaan 3 mission, and missions from other space agencies. And ascent has been shown by Chinese for their Chang'e in their Chang'e mission, and NASA has been working on Mars sample return, where they want to do test this ascent vehicle. Then you need enabling technologies, like even before human sets foot on the surface of these planets, you need very vast infrastructure of robotics. So for the exploration, and as of course, in situ research utilization is the another one which is needed for such long uh, missions here. So entry, descent, and landing and ascent. Let's look into what are the different types of entry and landing. So you need a lander, so which will either with aero assistance, as in case of Mars, you will be decelerating from orbital velocity to touchdown velocity. It has to come to zero, stand still. So you are traveling at around 1.6 kilometer per second, and you need to go to zero within a range of say around 750 kilometers, as you can see in terms of Chandrayaan. So, and these can be possible. This is possible by retro firing, rocket firing. And once you are very near to the surface, you cannot have a soft landing without landing gears. So the landing gears are very, very important. So which will give a feather touch or a touchdown, which will be very soft. And for this, like most of the systems, you do not have really any control over the last mission. So this has to be done autonomous. So this is where disruptive technologies or autonomous AI and ML from the other domains can really help the space domain in terms of reducing the mass, power budget, or communication requirements and computation. So this is where another technology area which will be needed. And finally, ascent. So either it can be an ascent of sample or human class ascent system. So you can see on the right hand side a typical landing based retro rocket firing landing you can see here. And now I just want to show a few videos of this lunar landing. As you can see, this you might have seen many number of times. I just want to, for the record, I just want to place it here. So how this particular landing is going to occur. So on the left hand side, you see the mission scenarios where it is separated, lander is separated from orbiter, and orbiter scans the lunar surface for possible landing sites and see a close range photography, which the lander itself does. And it figures out where exactly it is with respect to the landing site. And then the maneuvers takes place. And finally, you have a touchdown here. And on the right hand side, you can see this particular touchdown occurring in real time during the Chandrayaan 3 mission. So as you can see, the lander is hovering and finding out where exactly it can land. And finally, you will expect a touchdown, a very smooth touchdown, which was very successful in Chandrayaan 3. So this is typically what you expect when you land, and we have seen it's such a difficult technology, which like many agencies have failed, and only few agencies have this particular capability of landing. And this is the typical landing where you have an atmosphere, even though the surface atmosphere on Mars is only 1%, it is sufficient to decelerate. So as you can see, you need aero assistance based system where you create drag using this aerodynamic surface and reduce the orbital velocity. And as you come down, you open a parachute which has to work in supersonic range, and it should decelerate. And finally, the aeroshell is jettisoned, and the rover is like it starts looking for where to land, and backshell separation happens. And finally, this is a particular technology which NASA employs. It is called sky crane technology, where instead of landing and a rover coming out from the lander, so they wanted to directly land the rover onto the surface. So this is as like you can see the helicopter in most of the movies or rescue missions you might have seen. There is going to be a small bridle which comes out and picks up the person. So it is the reverse way of that, wherein which the sky crane bridle is extended through the rover, and it touchdown after the touchdown of rover, these bridles are severed, and the sky crane flies away. So this is a typical landing which is employed in Mars landing. Earlier, NASA had employed the airbag technologies, and it is found to be prone to failures. So they changed over the technology. So this is where what I was trying to make a point here is the technology change in one technology can affect or enable a very different scientific mission altogether. And this was a game changer for NASA in terms of delivering their rover. So I have shown here a picture. I request you to enjoy this particular video. As you can see here, in 2020 surface of moon. So the ones which I have explained, you can see the animation here. And finally, on the right hand side, you can see the actual videographs which have been transmitted back to Earth. So here you can see in the parachute. This is the real picture which is taken from the NASA. So as you can see, the back shell separates. These are not timed, so just wanted to show how this really happens in real time. So it is trying to explore where to land, and after that the bridle comes and it gets delivered, and this is flyer. It has been taken out, and the rover is ready to explore. And as you can see on the right hand side, it is looking for the landing site, and it is still coming down. And I will just, for saving the time, I'll just go to a point where exactly this particular event occurs. So as you can see, and you can see beautifully the dust getting like blown from the surface as the lander is near to the surface. So these are the three images or videos which have been taken. One from the rover itself, and the other one is a sky crane system. Yeah. So now NASA is working, as I told, on sample return mission. So a sample return mission, what happens is it is similar to that. The particular Mars 2020 rover which has been sent is been collecting these samples on the surface, and a rover which will load this sample onto the Mars ascent vehicle, as you can see here, and this blasts off. Yeah, and it blasts off and goes to the orbit, and the sample is collected and brought back to the Earth. Okay, now this I have shown about robotic land, I mean basically landing platforms which are needed. And now let us look at robotic exploration. So as you can see here, the rover in Chandrayaan 3 and beautifully captured by lander. And this became a very famous video wherein which it was looking for the path and scanning for where to go and which is the safe path for the rover. And on the right hand side, you can see one of the instrument being operated by this rover, which is called APXS, alpha particle X-ray spectroscopy. So which is used for making the measurements. You can see here a small dot here, so which gets stowed. So these are the kind of experiments which are generally carried by the robotic exploration, because the landing platform is a static platform. It will not be able to collect samples or do experiments outside its area. So when you need large surface exploration, so that is where you employ rovers, and it's a basically a geologist, or it can be a looking for signs of life, as in case of Mars. And like future is really exciting. So as you can see here, so this is one of the uh, it's a system of rovers which are going to be placed on the south pole of the moon, and these rover combined like with minimum intervention from the ground are going to do their own autonomous exploration and tell if they find something very interesting, then automatically they tell and inform, so that the ground infrastructure needed for such events will be less. So autonomy and robotics, it's going to be a very interesting decade. And the finally we want to have human presence there. And this is a one, because of paucity of time, I'll just uh, show this particular video where like typically what is needed for exploration of like human exploration of system. Like you need a very large cargo system, and you need a lot of ground support. Like you need a very large uh, landing system, and you need pressurized rovers to carry astronauts and do the experiments. And as you can see, you need to this is a rover which will be carrying the ferrying the astronauts to do their experiments and collect the samples, do the experiments in situ, and go from one habitat to the other one. So this is the ascent vehicle, which will be it's a launch pad from the surface of moon. So all these things are possible only when you have in situ research utilization. So what you can see on the left side is like this is 3D printed habitat, and this has been used using the lunar regolith. And when we go to the terrestrial other than our Earth, then the soil there it is called regolith. So that particular regolith is used to manufacture these artifacts. In the center, what you can see, you can print gears, screws, and all. So 3D printing or additive manufacturing is going to be the game changer. So as I keep telling, the technologies will enable very different missions which can be performed without spending much of the money. So that's where like cost effectiveness becomes very important. And this is one concept where additive manufacturing is used for construction of habitats. Now we have seen in the mission architecture and what is needed, but let's come to the at a like a lower level than whatever like mission architectures we have been seeing till now. So basically, you need a very good system engineering. So the system engineering is basically where they bring all the systems together, like whether it can be propulsion system, mechanical, mission, controls, and they have to deliver an optimal system for particular mission. So earlier it was all like the requirements and all these are done using paper-based approach. Now the model-based system engineering is becoming a very important tool, wherein which all these systems multi-physics modeling is used in order to arrive at system specification. So that's how we become very efficient in building the final architecture. And propulsion, advanced propulsion systems are needed. Electrical propulsion is going to be the way forward. And power. So power, if you go to Mars and all, you'll not be like you are still away from sun, so the power generation capabilities is less. So either you need to have some kind of geothermal power system or nuclear power system. In fact, the Mars 2020 rover, which I had shown you earlier, it has a nuclear powered system, so it does not have solar panel if you have seen them closely. And all these things are possible with the deep space communication, wherein which you need larger antenna systems, you need higher frequency band operation and for higher bandwidth, and ultimately deep space based atomic clocks are needed for navigation. So navigation is going to become very important aspect here. And all these things are possible if you can reduce the burden on earth system. That can be done using autonomy and health management. So these are all automatically takes care of itself. So the health monitoring which you can see in your own cars, which they tell tire pressure and all, where you can monitor, so you don't have to keep checking it, so it automatically detects and tells. And right now it is like done manually, so wherein which the autonomy is going to play a very big role if you want to have very price effective or economic missions. This is at system level. Now there are, of course, in the audience there are a lot of you who are in their 20s and doing their engineering So they want to know how I can contribute. Like I cannot be space agencies where I design the mission architecture and all. How do I contribute? So when you want to contribute for this particular mission or for this particular endeavor, then you can contribute in various ways by exploring these particular subsystem. As you can see on the left hand side, sensing and perception is going to be like when you have either it can be laser based sensing or vision based sensing. You need proximity sensing, pose estimation, velocity inertia estimation when you are docking two systems or doing in orbit assembly. Then you need terrain relative navigation. So this can be, in fact, the terrain relative navigation has been employed quite extensively, even in case of helicopters or the drone system which are being developed. And this is where you can, and sensor fusion and hand eye system. So these are some sample subsystem which I've been telling. So mobility system like map creation, it is in fact useful for even your own house. If, for example, you have a vacuum cleaner which has to work automatically, then it has to create a map. So that is where, and it will be similar. The technology will be similar, but computationally, since you need radiation hardened computational architecture, so how you can make them computationally efficient? So that is where you can contribute. Then you have a manipulation system where either like drilling system, lightweight structures. If you are a mechanical engineer, you would be very much interested in that. And autonomous docking. So you cannot have docking based on human intervention. So it has to have autonomous docking. Then you have, since humans and machines are going to work together, so you need human robot interaction system and autonomy. So these are some of the things. Like if you come here, then it is a system level at which maybe you can, a private agency or a government agency can come out with mission and deliver these things. And finally they will form a place in terms of rover, walking rover, aerial drone system, or docking system, human robot system, test facilities. So some of you can work in this area. So what is the secret recipe if you want to have a disruptive technology, which I want to share here? It's called Galileo methodology. What he did, he identified key scientific problems. He took existing technology, which was a telescope, and developed into a new level to make observations. And virtually, in fact, that has led to a scientific and technical progress. And it has enhanced both science and engineering. So science and engineering have to have go in hand in hand. In fact, that's how you are going to have a disruptive technology, and that is how Galileo is considered to be disruptive. So coming to the last slide, development of disruptive technologies, you all are invited in this endeavor. In fact, you can contribute wherever you are in terms of as a human species to make new discoveries and new worlds to explore. With this, I conclude my presentation here. Thank you. Thank you all.